Okay. Ordinary differential equations time. Any questions before we start? Or we can start with questions. So we're studying first order equations. That means differential equations where the highest derivative is the first derivative, and the first topic are linear equations. So what I'm going to do is go through a proof of the existence and uniqueness of solutions to such equations, and then I'll do a couple of the homework problems. So let me switch to my writing pad. So let's see if I can set this up properly. Let me just make sure everyone is muted. Good. Okay, so if we have a first order linear ordinary differential equation, there's an unknown function y, and its first derivative is in the equation y prime, and linear means y prime plus some function p of x times y equals f of x. That's the general form of a linear first order ordinary differential equation. And we say this equation is homogeneous if the right-hand side is 0, and non-homogeneous if the right-hand side is not identically 0. And there is a method to solve all such differential equations, which I will show you and prove for you right now. Now, sometimes we have to find the general solution, and sometimes there is what is called the initial value problem. Find the particular solution. That means a particular function y of x such that at some initial value x naught, the value of the function is some fixed value y naught. So this is an initial condition. So there are in general two problems to solve. One is to find the general solution of the equation. And then if you're given an initial value, initial condition, to find the particular solution. So let me first describe the method to solve the homogeneous equation. So the homogeneous equation is y prime plus p of xy equals 0, where the function p of x is continuous on some open interval from a to b. Right? So you're given a function p of x, which is continuous on an open interval. Open means this is the set of points x, where x is strictly greater than a and strictly less than b. So this open interval is the set of all x, which satisfy the strict inequality. So we don't include the endpoints. P of x may be continuous at the endpoints. P of x might be continuous on the whole line, but that's irrelevant. What we need is some particular interval on which the function is continuous, and we're solving just on that interval. We can change the interval and get a different problem, but we're given the differential equation with the continuous function p of x, continuous on some open interval. And so there is this, what you might call the trivial solution, which is just y of x is equal to 0 for all x. Because if y is identically 0, the derivative is 0, and you get 0 plus 0 equals 0. So that's always one particular solution, but it's not the only solution. So how do we find a non-trivial solution? Well, one thing we can do is to let capital P of x be the antiderivative of the function little p of x dx. So that means that capital P prime of x differentiated gives you little p of x, right? That's the indefinite integral. And if we let y be c e to the minus p of x, right? So you have the function little p, you integrate it, you get capital P. Look at this function. So what is y prime? Y prime, by the chain rule, is minus capital P prime of x, c e to the minus p of x. But capital P prime is little p. So this is minus p of x, and this is y. So we get y prime plus p of x y equals 0. So this is another solution of this differential equation. And you notice that in this case, y of x is different from 0 for all x if c is not 0, because the exponential function is always strictly positive. It's never equal to 0. So we found the trivial solution, y identically 0, and we found a non-trivial solution. And I claim that these are the only solutions of this equation. Right? So this shows there exist solutions, but how do we find a non-trivial solution? Sorry, how do we prove these are the only solutions? So suppose y of x is a solution of the equation y prime plus p of x y equals 0. So p of x is continuous. Sorry. So y of x is the solution of this equation. So if y of x is not identically 0, then y of x is different from 0 for all x in some subinterval of a, b. That is, we have this interval from a to b, and y is some function defined in this interval, and y isn't identically 0. So there's some point x where y of x is non-zero. It's either positive or it's negative. And y of x is continuous because it's differentiable. So if it's not 0 at some point, it's not 0 in some interval around that point. So there's always some subinterval of the interval from a to b where y of x is not 0. So if it's not 0, you can divide by it. So if we have y prime plus p of x y equals 0, that's the same as y prime equals minus p of x times y. And dividing by y, we get y prime over y is minus p of x. Right? We're allowed to divide by y because y of x is not 0. And then you integrate. The integral of y prime over y dx is the integral of minus p of x dx. And you learn in calculus that the integral of y prime over y is the log of the absolute value of y. And if we let this indefinite integral p of x, call that capital P, this is minus p of x, plus some constant. P of x is some particular antiderivative of little p of x. So if you exponentiate, you get the absolute value of y is e to the k, e to the minus p of x. And again, on this interval, y is either always positive or always negative. So y is plus or minus e to the k, e to the minus p of x. And I can let e to the minus, plus or minus e to the k, that's just some constant c, e to the minus p of x. So what this says is that every non-zero solution of this differential equation is of the form c e to the minus p of x, at least on some interval from a to b. But p of x is defined and continuous everywhere from a to b. So this solution extends to a solution for all x between a and b. So this is a proof that every solution of this differential equation is of this form. In fact, of this form, even if it's the trivial solution, because if you can choose c equals 0, and you get y is equal to 0 for all x. So that's a proof that the solution of the homogeneous equation is always a function of this form. Okay. Now, any questions about that? So let me do one or two of the homework problems, the ones that are due, I guess, next Monday, which are solutions of homogeneous differential equations. Let me take, for example, let's see what looks interesting. Number 2. So this is on page 41, number 2. Find the general solution of y prime equals 3x squared. Sorry, y prime plus 3x squared y equals 0. So this is of the form y prime plus p of x y equals 0, where my function p of x is 3x squared. And capital P of x is the integral of 3x squared, which is just x cubed plus any constant. Or that's enough just to write down x cubed, one particular solution. So my solution y is equal to c e to the minus p of x, or c e to the minus x cubed. That's the solution of this differential equation. And you can check if y is c e to the minus x cubed, y prime is the derivative of minus x cubed minus 3x squared c e to the minus x cubed. But c e to the minus x cubed, that's y. So this is minus 3x squared y. So y prime is minus 3x squared y. So that means that y prime plus 3x squared y equals 0. Any questions about that? All right, let's look at another one. Let's look at number 3.
Can you do number 7, if it's possible?
Number 7? Yeah, I'll get after
Yeah.
that. I want to do like sort of easier ones and sort of build up. But I'll definitely do number 7. Number 3 is the equation xy prime plus log x times y equals 0. And you might say this doesn't look right because in my general form for a linear equation, the coefficient of y prime is 1. And here it's not 1, it's x. But we can deal with that easily. For x different from 0, divided by x. So we get y prime plus log x over x times y equals 0. And log x over x is defined in continuous. Well, the logarithm is not defined for 0 or for negative numbers, but it's certainly continuous on the whole interval from open interval from 0 to infinity. So that's my function p of x. So capital P of x is the integral of log x over x dx. And what's the integral of log x over x? Let's see. If you make the substitution, u equal log x, so du is 1 over x dx. This becomes the integral of u du, which is a half u squared. And that's a half log x squared plus a constant. And you can check. The derivative of a half log x squared is a half times 2 log x times the derivative of log x, which is log x over x, just what it's supposed to be. Right. So the solution of the differential equation, the general solution is y equals c e to the minus p of x, which is c e to the minus a half log x squared. Let's check if this is in fact correct. If y is c e to the minus a half log x squared, dy dx, or y prime, you differentiate the exponent, you get minus a half times 2 log x times the derivative of log x, which is 1 over x, times c e to the minus a half log x squared. The 2's cancel. This is minus log x over x times y. And that was exactly the differential equation we started with. Just bring this over to the other side. Y prime plus log x over x times y equals 0. Okay. Any questions about this? Now you might say, suppose I can't do the integral. Here we had to integrate log x over x. What do I do? And the answer is, I guess, dig up your old calculus book and start to study review integration. Because you need to do integration. Math 176 is necessary to solve these differential equations. You have to be able to do these integrals. Right? Questions about that? Okay, someone asked me about number 7, which is an initial value problem. So problem number 7 on page 41 is xy prime plus 1 plus 1 over log x times y equals 0. And we want to solve the equation with the initial condition that at x equal to 1, y of 1 is equal to 1. So this is an initial value problem. Now again, the coefficient of y prime isn't 1, it's x, so you have to divide by x. You get y prime plus, so this is for x positive. Log x is only defined for x positive. 1 over x, 1 plus 1 over log x times y equals 0. So we have, this is my function p of x. P of x is equal to, just multiply through 1 over x plus 1 over x log x. Okay. So this is the starting point. Are there any questions about how I got from my, in the given differential equation to it in the standard form, but dividing by x? And now I have to integrate. Capital P of x is the integral of little p of x dx. That's the integral of 1 over x plus 1 over x log x. The integral of 1 over x is log x. And the integral of 1 over x log x is log x. So this is a particular antiderivative of this function. So my general solution is y equals CE to the minus P of x. What is that? That's CE to the minus log x plus log x, which is CE to the minus log x, e to the minus log x. E to the log x is x. So this is C x to the minus 1. E to the log x is log x to the minus 1. Or C over x log x. This is the general solution of this equation. Y equals C over x log x. How do we solve the initial value problem? Oops, sorry, I wrote down that the initial value problem was y of e is equal to 1. So y of e, when you let x equal to e, you get c over e log e. Log e is 1. This is c over e, and we want this to be equal to 1, which means c over e is 1, c is equal to e. So my solution to the initial value problem is y is equal to e over x log x. And you can, again, you check, you plug in x equal to e, you get 1. So let's check this is also a solution to the differential equation. So if y is equal to this, so we have y is equal to, let me write this as e, x log x to the minus 1. So when you differentiate y prime, you get minus e x log x to the minus 2 times the derivative of x log x, which is the derivative of x, which is 1 times log x, plus x times the derivative of log x, which is 1 over x. So we have y prime is equal to log x, and this is 1, right? This is minus e log x plus 1 over x log x squared. Is this the solution of this differential equation? Let's see. Let me multiply by x. Because in my original equation, I had xy prime. So let me multiply by x. So xy prime is equal to minus e log x plus 1 over x log x squared. E over x log x is equal to y. So let me write this. This is minus e over x log x times log x plus 1 over log x. This is minus, this is log x over log x, which is 1, plus 1 over log x, times e over x log x, which is y. So that's exactly right. Xy prime plus 1 plus log x times y is 0. So this checks. Okay. Any questions about this? So these are the types of problems that you have to be able to do. Now, these are all, these homework problems for Monday, problems 1 to 8, are all homogeneous problems. And I need to now show you how to solve non-homogeneous problems. So let's start with perhaps an example, maybe to make it a little bit easier when you're studying. I'll start with one of the examples that's in the text. So this is example, so on page 35, this is example 2.1.5. We have the non-homogeneous equation, y prime plus 2y equals x cubed e to the minus 2x. So if you think of the general form of the linear equation being y prime plus p of xy equals f of x, in this case, my p of x is equal to 2, and my f of x, the right-hand side, is x cubed e to the minus 2x. So the first step is to consider what is called the complementary equation, which is the homogeneous equation you would get if you set the right-hand side equal to 0. So the homogeneous equation, the complementary equation, would be y prime plus 2y equals 0. And suppose you let y1 be a solution of this equation, a particular solution. So for example, y1 can be e to the minus 2x, right? If you have y prime plus 2y equals 0, you learned in Calc 2, second semester calculus, that a solution is any constant times e to the minus 2x. All right, and now we want to use a technique which is called variation of parameters. So we want to look for a solution of the form y equals some function u times this function y1. So y1 is a particular solution of the homogeneous equation, the complementary equation, and u is some function to be determined. So we're going to look for a solution of the non-homogeneous equation, which is a solution of the homogeneous equation, y1, times some other function. Now, if y is u times y1, by the product rule, y prime, it's the derivative of, derivative of u times y1 plus u times y1 prime, right? So if you plug this into our equation, y prime plus 2y, that's u prime y1 plus u y1 prime, plus 2 times y, which is u y1. We want to find a u such that all this is equal to this right-hand side, x cubed e to the minus 2x. If you look at this for a moment, you see, what do you have? You have u prime y1 plus u y1 prime plus 2u y1, I factor out the u, y1 prime, plus 2y1 equals x cubed e to the minus 2x. Right? I just rearranged this equation. But y1 prime is a solution of the complementary equation. y1 prime plus 2y1, this is equal to 0. So that term disappears. And we just get u prime y1 equals x cubed e to the minus 2x. So u prime, and what is y1? y1 is e to the minus 2x. So we have u prime e to the minus 2x equals x cubed e to the minus 2x. E to the minus 2x cancel. U prime is x cubed. So then you just integrate x cubed. So u is the integral of x cubed, which is a fourth, x to the fourth, plus a constant. So y, which is uy1, is 1/4 x to the fourth plus a constant times y1, which is e to the minus 2x. Or if you like, this is x to the fourth e to the minus 2x over 4 plus c e to the minus 2x. And lo and behold, we solved the problem. This is the general solution of this non-homogeneous differential equation. So again, if you look at all differential equations, the simplest are first order. If you look at all first order equations, the simplest are linear for first order. And we now have at least the germ of an idea how to solve such an equation. Okay. Any questions about this? So let me just show you that the method we use here works in general, and I will prove the basic theorem about how to solve a non-homogeneous first order linear differential equation. So this is the basic theorem at the beginning of our course. You find it stated on page 40, theorem 2.1.2. So we have functions p of x and f of x, continuous on an open interval from a to b. Let y1 be any non-trivial solution. That is not the zero solution, any non-trivial solution of the complementary equation y prime plus p of x y equals 0. The general solution of the non-homogeneous equation y prime plus p of x y equal f of x on the interval from a to b is given by the following perhaps scary looking formula, but it's easy in practice. It's y is equal to this particular solution of the complementary equation times an arbitrary constant c plus the antiderivative of, or the integral of f of x over y1 of x dx. And you might ask, how do I know I can divide by y1? And that's because we saw that for the solution of the homogeneous equation, the solution is never zero. On any open interval, it's either always positive or always negative. You can always divide by y1 of x. So how do we prove this theorem? So there are two steps. First is to show that this is a solution. And the next step is to show it's the only solution. So suppose we have this formula, right? I claim that any solution of this form, that is, for any particular solution y1, any constant c, this is a solution of the non-homogeneous equation. So the first step is to check that this function I gave a start to is a solution. That means you have to differentiate y. So y prime, by the product rule, is y1 prime of x times c plus the integral of f of x over y1 of x dx, plus y1 of x times the derivative of this. The derivative of a constant is 0. The derivative of the antiderivative is f of x over y1 of x. You'll notice that y1 and y1 cancel. So what we have over here is just f of x. And what do we know about y1 prime? Y1 prime is a solution of the homogeneous equation. That is, y1 prime plus p of x y1 is 0. So y1 prime is minus p of x times y1. So this is y prime is minus p of x y1 times c plus the integral of f of x over y1 of x dx. Plus f of x. Y1 of x times this is y. So you get y prime is minus p of x times y plus f of x. So if I just bring this over from the right to the left-hand side of the equation, y prime plus p of x y equals f of x. So this is always a solution of the differential equation for every c. So this tells us this differential equation has a solution, and this is a formula for how to find it. I claim that, in fact, every solution is of this form. That's the uniqueness part. There exists a solution, here it is, and it's unique for any given initial value of these. So let's prove that second part. So we have the following, that y be a solution of the linear first order differential equation y prime plus p of x y equals f of x. So let y1 be a solution of the complementary equation y prime plus p of x y equals 0. So if y is the solution of this equation, y1 of x is different from 0 for all x. So we can always divide by it. So let u of x be y of x divided by y1 of x. So then y of x, or y, is u of x times y1 of x. And y is the solution of this differential equation. So y prime plus p of x y, differentiate y, you get u prime times y1 plus u times y1 prime plus p of x times y, which is uy1, is equal to f of x, because y is a solution of this differential equation. And here, if I factor out a u, I get u times y1 prime plus p of x y1. But this is 0. So this term disappears. So u prime y1 is equal to f of x. So u prime is always equal to f of x over y1, which means u is the integral of f of x over y1 dx plus a constant, which means y, which is u of x, y1 of x, or uy1, is this times y1. It's y1 times the integral of f of x over y1 dx plus a constant. And that's what we wanted to prove, that every solution was of this form. So this says we can always solve a first order linear differential equation. Not only that, but we can solve every initial value problem. So
Professor, can you go back to the last page?
yes. Again, this is all in the book, and everybody has the book because it's loaded on Blackboard. So this is the proof of theorem 2.1.2 on page 40.
Thank you.
So if you have y prime plus p of x y equal f of x, the general solution is y equals a solution of the complementary equation times an arbitrary constant c plus the integral of f of x over y1 of x dx. And suppose we have the initial value problem. We want y at some value x naught to be equal to y naught. This simply gives you an equation that you just have to solve for c. You would get y of x naught, you get y naught, which is y of x naught, is y1 of x naught times c. Let's just take a particular integral. Let's make this the integral from x naught to x. So the integral from x naught to x naught f of x over y1 of x dx. This is 0 when you integrate from x naught to x. This is c y1 of x naught. So you just let c be equal to y naught over y1 of x naught. Right. So this might seem a little bit abstract, but if you work problems, it becomes concrete and simple, I hope, very soon. So let me spend a few minutes now solving a non-homogeneous equation. And let me take, for example, on page 41, a very simple looking equation. This is problem number 12. Y prime plus 3y equals 1. Find the general solution of this equation. So the coefficient of y, p of x, that's just 3. And the right-hand side function is just 1. So we have a constant value function p of x and a constant function f of x. So what is the complementary equation? y prime plus 3y equals 0. Solution of that is, a particular solution is y1 equals e to the minus 3x. We're going to let y equal u times y1, or some function u times e to the minus 3x. If we plug this into the equation, y prime plus 3y, when you differentiate this, you get u prime e to the minus 3x minus 3u e to the minus 3x plus 3y, 3u e to the minus 3x. We want that to be equal to 1. Of course, what we have here, this is u times minus 3e to the minus 3x plus 3e to the minus 3x. So this is clearly equal to 0, right? Minus 3 plus 3 is 0. That disappears. So u prime e to the minus 3x is 1. So the derivative of u is e to the 3x. So u is the integral of e to the 3x dx, which is a third e to the 3x plus a constant. So the general solution is y equals u e to the minus 3x is 1/3 e to the 3x plus c times e to the minus 3x. That's equal to c e to the minus 3x plus a third e to the 3x times e to the minus 3x. That's just 1. This is y. That's the general solution. Right? And this 1/3 is critical. Right? It's c times this plus a third. So I claim this is the solution to the general solution to the non-homogeneous equation. Let's just check. So this is y. So y prime is minus 3c e to the minus 3x plus 0. So y prime plus 3y is minus 3c e to the minus 3x plus 3 times y, c e to the minus 3x plus a third. This is equal to minus 3c e to the minus 3x plus 3c e to the minus 3x plus 3 times a third. These cancel, and 3 times a third is 1, which is what it's supposed to be. So this is correct. Okay. Any questions about this? This is basic technique for ordinary differential equation. Let me solve an initial value problem.
1 second.
Yep. Again, this is all recorded and it'll be posted on YouTube within an hour or so, depending on how slow the internet is.
Thank you.
Okay. So what about an initial value problem for a non-homogeneous equation? Let's look at number 25. Suppose I want to solve the equation y prime plus 7y equals e to the 3x, with the initial condition that y of 0 is equal to 0. So my function p of x is equal to 7, and my function f of x is e to the 3x. So let me start with the complementary equation. Y prime plus 7y equals 0, and a particular solution is y1 equals e to the minus 7x. And I'm using the technique of variation of parameters. I want to let y be a function of the form u times y1. So u is this unknown function I have to determine. So if I plug this into this equation, y prime plus 7y, so and u is uy1, this is u e to the minus 7x. So y prime is u prime e to the minus 7x minus 7 times u e to the minus 7x plus 7 times y, 7 u e to the minus 7x. And again, this is 0, this cancels. So this is just u prime e to the minus 7x. And this is supposed to equal e to the 3x. So that's easy. U prime e to the minus 7x equals e to the 3x. That means u prime is e to the 10x, just multiplied by e to the 7x. So when you integrate, u is equal to 1/10 e to the 10x plus a constant, which means my general solution for this equation, y equals u e to the minus 7x, that's 1/10 e to the 10x plus c times e to the minus 7x, or if I expand this, I get e to the 3x over 10 plus c e to the minus 7x. So this is the general solution of the differential equation. And we want to find the particular solution where y of 0 equals 0. So 0 has to be the function y evaluated at 0. When you let x equal 0, you get 1/10 plus c. So c is equal to minus 1/10. So my particular solution is y is equal to e to the 3x over 10 plus c, which is minus 10, minus e to the minus 7x over 10. And that's it. And again, you can check when x equals 0, you get 1/10 minus 1/10, which is 0. So this satisfies the initial condition. And it works. Let's just check that this really does solve the differential equation. So this is y. So y prime plus 7y. If I differentiate y, I get 3 over 10 e to the 3x. Differentiate this, I get a minus 7 plus 7 over 10 e to the minus 7x plus 7 times y plus 7 over 10 e to the 3x minus 7 over 10 e to the minus 7x plus 7 over 10 minus 7 over 10. They cancel. 3/10 plus 7/10 is 1. This is e to the 3x. So this does check. Right, any questions about this? Let me do just one more problem and then I think that's enough for today. Let me do another non-homogeneous initial value problem. Let's just do the next one. So this is on page 42, number 26. So we have the differential equation 1 plus x squared times y prime plus 4xy equals 2 over 1 plus x squared. And the initial condition is y of 0 equals 1. So again, this isn't in exactly the right form because the coefficient of y prime isn't 1, it's 1 plus x squared. But 1 plus x squared is always positive, so you can divide by it. So we rewrite the equation, you get y prime plus 4x over 1 plus x squared y equals 2 over 1 plus x squared squared. Okay. And the complementary equation is y prime plus 4x over 1 plus x squared y equals 0. So this is my function p of x. Capital P of x is the integral of 4x over 1 plus x squared dx. And this is, I believe, 2 times the log of 1 plus x squared. If you differentiate this, you get exactly that. So my particular solution of the complementary equation is y1 equals e to the minus 2 times the log of 1 plus x squared. What is that? This is like 1 over e to the log of 1 plus x squared squared. That's 1 over one plus x squared squared. And so if we're going to let,
Professor,
yeah,
for the specified questions you're doing, it says you need to graph a picture of the solution.
right.
Are we not doing that, or do?
Well, so for example, for the previous problem, you had the solution y is equal to e to the 3x over 10 minus e to the minus 7x over 10.
Mm-hmm.
So e to the 3x over 10 is something that looks like that. And when x equals 0, it's a 10th. This is a decaying curve. E to the minus 7x over 10 looks like that, minus that looks like this. So when you put the two of them together, you're going to get something which looks like that. And that's the best you can do by hand. If you have a graphing calculator or a computer or Maple, you can graph it more carefully. But you know, it's just a matter of getting it. Yeah. So that's what the graph would look like.
Okay.
I mean, that's the best you can do without using a computer. Okay. Yeah, okay. So this is y1, and if we're going to let y be some function u times y1, then let's just go back and look at what our theorem tells us is the function u. U is the integral of f over y1. So if we're going to let y equal u y1, u is the integral of f of x, this is f of x, 2 over 1 plus x squared squared, divided by y1, which is 1 over 1 plus x squared squared. That's just the integral of 2 dx, which is 2x plus a constant. So looks like we're very lucky here. Right? F of x is 2 over 1 plus x squared. Oops, sorry. Yeah, f of x is 2 over 1 plus x squared squared. y1 is 1 over 1 plus x squared squared. The quotient is 2. The integral of 2 is 2x plus a constant. So we get as our general solution, y is 2x plus a constant times u. That means over 1 plus x squared squared. That's the general solution to this differential equation. And if we let x equal 0, we want y of 0 equal to 1. 1 equals y of 0. When you let x equal 0, you get c. So c is equal to 1. So the particular solution to this equation is 2x plus 1 over 1 plus x squared squared. That's the solution of the initial value problem. And to graph this by hand, when x is 0, it's equal to 1. As x goes to, and this is positive for x greater than 0. And it's decaying to 0 because this is a linear over a quartic. So this is whatever it does in the middle, it's decaying down to 0. And as you go to minus infinity, it's see, when x equals minus a half, it's 0, and then somehow looking like this. But that's really about the best you can do, drawing these things by hand. Okay, any questions about this? So I had posted on Blackboard, if you do have some questions that you want me to work out, I'm having problem sessions. I think I said Thursday and Friday, tomorrow and Friday at 12 o'clock. And if you have a question, any sort of question, want me to do a homework problem or whatever, you're welcome to log on at one of those times and ask me. It's just a general problem session for a couple of classes that I have.
For those, would it be okay even to go back to previous questions on previous homeworks or just previous chapters, or?
In the problem sessions?
Yeah.
Oh, you can ask me about anything at any time.
Okay, so I will see you tomorrow then.
Okay, very good. Very good. Any other questions? Anything else I can do before we quit?
Professor,
Yes.
you haven't posted the link for the office hours.
Oh, it's the same Zoom as for the class. It doesn't
Okay, got
change.
it.
It's for,
Okay.
I have one Zoom for all my, I mean, otherwise it's too complicated. So
Got
Gotcha.
it.
it's just one Zoom for the semester.
Okay, so the office hour starts at 12 or?
Yeah, it starts at 12. I
Okay,
mean,
got it.
it's not exactly an hour because if I log
Yeah.
on at 12 and no one is there and I hang around for half an hour and no one is there, I go off and eat lunch.
Okay,
Okay.
Right, but on the other hand, if you do log on at 12 and you have 2 hours worth of questions, I'll stay around for 2 hours. But yeah, 12 o'clock is the scheduled time. Okay. All right, everyone. Enjoy the rest of the day. We have regular class again on Monday. Bye all.
thank you so much, Professor. Have a good day.
Thank you. You too.